Hi, welcome everyone. So in the previous video, we discussed on how the P-delta effect come into the picture and how it is related to the buckling point. Now also we had discussed the iterative solution path by doing a set of iteration to determine the final P-delta response like movement and displacement. So one thing we understood that any kind of initial imperfection like out of plumbness or eccentric loading that could lead to the generation of additional moment can trigger the P-delta effect. Now, this P-delta effect can also be due to the member initial crookedness or a curvature, which we call it the member imperfection, which is also known as the P small delta. Now, this is the P small delta. So this P small delta can also add the secondary moment due to small lever arm distance. So in short, no axial member in the real life scenario is perfectly or ideally straight. The perfectly or ideally straight that we only model in the software, right? But in real life scenario, that doesn't happen. There is always some proportion of initial imperfection like crookedness or curvature which can add the initial second order effect to trigger the P delta solution. And this solution could eventually tell us if the solution is converging or diverging. So if it is diverging, then we can understand that the system has already buckled. So you could notice from this entire discussion that the buckling behavior all starts from the combined axial plus bending phenomena. Now today in this video we will understand another way to capture the P-delta effect without doing the iteration. Now instead most of you who have used the P-delta analysis before must have noticed two different procedure. One is the iterative P-delta analysis and another is non-iterative by selecting the P-delta KG option. Now this is known as the one-step solution path. So basically, this is known as the P-delta KG matrix procedure or geometric stiffness matrix procedure. So we will see by a simple example to understand how this P-delta KG matrix can be formed and how we can use it for the one-step solution. And later we will try to understand its direct relationship to find the buckling factor and the buckling mode shapes. So here we are taking a simple system. This is a standing cantilever, but it's not exactly cantilever. We are just modeling as a straight column whose base is pinned. This is a simple example we are creating to make you understand how the P delta KG matrix can be formed or how it can help us in this one-step solution path. This is a spring connected laterally and this is load P acting at the tip. Now by this red color we mean to show the displaced position and this X is denoting the final displaced position and the stiffness of this spring is K. This is the length and this is the lateral force provided at the tip. Now, in our previous video, we have made it somewhat similar, but not exactly the same. We have denoted the stiffness of this column through this spring at the tip, but In the previous video, we have just kept it as a cantilever column. So here the restoring force in this case is attributed by the spring, but in the previous scenario where we have modeled the cantilever column, the restoring force is due to the bending stiffness of that column. Now, if we want to find the equilibrium of this entire system, it is very simple. Just if I take the moment about this node, it will be like F times L plus P times X minus Kx times L equal to 0. So these are all the moment about this point, right? Kx is the extension of the spring, and this is the lever arm distance. And this all boil down to the 0 value because at this portion we have imposed a pin joint, and the moment at the pin joint would be 0. So if we just rearrange this, we will. So after rearranging, we can get this term. So basically here, this applied force F, and this is the displacement. In general, we could determine it by F equal to K times L, that is the stiffness of the spring. But here you can see this term has also got inside. And this term is also representing the stiffness, lateral stiffness. So we can say that this is like K into kg times x, and this kg is P by L. So what we can understand from this entire expression, that this lateral displacement is related or is dependent on the actual stiffness, lateral stiffness, and also a variable stiffness kg, which is a function of the applied load. And this term is known as the kg term, or we can also term it as geometric stiffness, and also we can term it as a stress stiffening. Now this is a model which is having a single node. We can have an entire system or a frame where this would be reduced to some matrix form. This K could be reduced to this one, and Kg would be reduced to this. Okay, so we will discuss later. So this stress stiffening effect is a very interesting effect. So that means if we are applying the load P vertically, the overall stiffness under this expression get reduced. Overall stiffness means the lateral stiffness, lateral load resisting stiffness. Now it could be the other way around. If we reverse this loading action, for example, the P is acting upward. Now, if the P is acting upward, then we can define this term instead of this plus, it would be like minus. And when it would be minus, we can get this term as plus, 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 and plus, and so on. That means if the load is acting upward, then my overall stiffness gets improved. Okay, so it can be bifurcated as a stress softening or stress hardening effect. So when there is a tension, it would be like stress hardening, and when it is under compression, it will provide the stress softening effect. Now, this has got a very significant physical interpretation. For example, this is a tight, stretched string. If you are providing some initial tension of significant magnitude, then you could notice that you can also stand on its top. It can carry a significant amount of load because we are stress hardening in this element. On the other way, if this is considered as a slender stick, just like a broomstick, and if you apply immense pressure at its top, then you might have noticed just by applying a slight nudge would destabilize this stick. That means due to this huge magnitude of the axial load, there is a stress softening effect, resulting which there is a very little requirement of lateral force to destabilize or collapse this system. So from here, we would derive the P delta kg and its involvement in the entire P delta solution path. So we are deleting this. This was the graph we discussed earlier, that is P and that is delta or displacement x. If it is a linear one, the graph would be like this. And if it is a non-linear one, it would be like this. Sorry for my bad sketch. Okay, this is the PCR. Okay, now there is a very interesting thing to discuss. Now, in the linear analysis, we are following this path or this relationship. Because it's a linear, there is a very proportional relationship between the applied load and the displacement. And this proportionality is maintained by the value called stiffness, that is K. So for this one, the stiffness is K. And for this one, this stiffness is varying. When we have generated this curve in our previous discussion, we have seen that we have selected different P loading, right? And we have done the iteration. So basically at every point, this slope, because this slope represents the stiffness, this slope is getting changed, right? So for certain P load, for example, we are applying a P load of P1, which is resting at here, somewhere at here. So at this P load, we want to know the displacement, that is the overall displacement, including the second order effect, that is the P delta effect. So we could either go by the iterative way, or else if we do not want to traverse this path step by step, what we can do is we can also somehow try to find a graph like this. It will be straight because it's a freehand sketch, so it's a little bit of curvy, which would connect the end point straight from the starting point. Or maybe if I connect this one. So what we can interpret from this graph, that somehow if we know this value, this slope value, then we can directly know the final response like displacement or shear or the moment, rather than going by step process through this graph. Now, if you carefully notice that this graph is nothing but this is the representation of K plus kg. K is the actual slope that we have determined for the first order analysis, but this kg is the shift from the initial path due to the inclusion of the second order effect. So the slope has shifted from this point to this point, right? entire slope has changed from this angle to this angle, right? So this kg is nothing but this angle is kg. Now, obviously, graphically, you can't determine the value of this kg, just it's a representation, like how we can do some one-step solution by just finding this kg and directly solve the relationship between p and k plus kg to determine the value of the response. Now, just to give you some idea, like this red curve ultimately has reached this point where we are interested to find the solution. If you are interested to find the solution here, this blue line would end here, um, because you can see there are two different paths to reach the solution. One is through the actual nonlinear path and the iterative, and one is straight way to reach this solution path. So basically, this path has been pulled down right side, right? Due to the effect of P. P means acting downward for this curve. Now, when the P is acting upward, now if I choose the path like this, then it is also diverting from the actual linear path, but in the opposite direction. So what this graph is representing? This graph is representing the stress hardening effect. So all the graphs on the right side of this slope denotes stress softening, and on the left side it denotes the stress hardening. So you could understand the graphical representation of this nonlinear path. Now our job is to find this final k plus kg value or this slope to directly get the solution point. Now here you can see that these kg can be directly derived from this relationship for a very simple model. But not all the models are that simple. So you need to form this kg matrix, which is dependent on the applied load. So this kg is variable and this k is a constant term. So you can refer to any advanced finite element books or any book on the advanced structural analysis where you can find the detailed procedure to derive this kg matrix for a beam element, for a plate element, and also for any kind of other element which is having multiple degrees of freedom. So this is the simplest example that I could explain. What is the interpretation of this kg and how this kg element can help us in getting the one-step solution to get the P delta response. Okay, so I'm rubbing this if you have noted them down. Okay, so our initial applied load was along the downward direction. Now, the equation that we have formed from this one, this simple arrangement is, so this plus and minus varies on the direction of the applied load P. So if it is compressive in nature, it would be minus. If it is tensile in nature, it would be plus. So I'm assuming it is pointing downward. So this was our actual equation. Now, this is just a normal expression for this simple system, but had it been a complex system, then this means the system with multiple degrees of freedom. This K would be represented as a stiffness matrix, normal stiffness matrix, and this would be represented as a kg matrix. And this X would be represented as a vector, displacement vector, and this F would be represented as a load vector. Now, let's take a simple example here. Now, this F is dependent on this kg value, right? Because kg is a value which is dependent on the applied load P. So more you apply the load P, the kg value would be increased. Now, if you look this equation carefully, you could understand that as this F is dependent on this entire expression, so we can find a relationship between this F and this P. If a situation arises that we keep on increasing this value of P and this F is getting decreased because this term is getting increased and eventually this term would come very close to this K value, right? And then this F is going to get diminished. Now, if we are increasing the value of P and it reaches to certain point when this F become minuscule, that means we need a very minuscule magnitude of lateral load to destabilize the structure at the tip, and then the entire system would collapse or buckle. So that means we need a value of force which is close to zero. So if we keep this value as zero, that interprets this term would also be zero. X could be infinitely high. This should be also equal to zero. This term, considering it as zero, means the stiffness is reduced to null. That means there is no lateral stiffness at all, right? So you can understand that if my resultant stiffness is zero, that means I need a slightest of nudge to just apply at the structural tip to destabilize the structure, or we can impart the structure to collapse. This is the point where the buckling arises. So buckling means you although need zero amount of load, but actually it's not zero, slightest amount of lateral push or slightest amount of a second order moment would be there, and that would be enough to destabilize the structure because in real life scenario there would be a slightest of lateral sway or some eccentric moment or some out of plumbness. So that would be enough to destabilize the structure and where the buckling would arise. So if we go by the matrix form, this would be like, so determinant of this matrix would be equal to 0. Okay, that is where the buckling happens. Now instead, we can directly solve this equation, but we have to solve this equation under some fixed applied load. You must have seen that instead, if this is a cantilever column and you are applying a load P and performing the buckling analysis, there are two different way to perform the buckling analysis. In the previous video, we have shown that you can do the buckling analysis by the iterative way, and another is the buckling analysis by the one-step solution that is the based on this KG matrix, or we can call it the eigenvalue problem. Now, if we do by this KG matrix procedure, then we have to solve this equation. But this KG is, as I have mentioned, it is dependent on this P. So we have to perform the buckling analysis with some fixed load P, right? So we are not incrementing this P load in this case. So what we can do is we would make this matrix like this and put a factor, it's an unknown factor just before this and equate it to 0. Okay, that means it will give me some idea like how much magnitude of the existing load P I need to amplify or scale up to get the buckling point. So if my load is P, this factor would tell me that I need to amplify by the amount of this value to my existing P to get the buckling load. So if my lambda is like greater than 1, that means buckling not happened under the existing load. And if it is less than 1, that means buckling already happened. Happened means under this existing load P. So you can understand from this entire discussion like P-delta analysis has got two different solution path. One is iterative and another is non-iterative. Iterative is the solution path by step procedure, and another path is by directly finding this K plus Kg, that is the resultant stiffness, and we can directly find the solution at the applied load P. So by both this procedure, we can find the P delta response at certain load P, and also we can find the load at which the system or the member would buckle. So in the next video, we will see the syntax that we need to apply in Staad to perform the P-delta analysis, both for the iterative and the non-iterative. And then we will just touch upon the different commands or procedure to perform the buckling analysis.